the way he explained that particular set of electrons revolving around the nucleus meant that they would radiate energy over the course of time and slowly spiral out of control and land in the nucleus. The angular momentum L of that particular electron will be equal to an integral multiple of h by 2 pi, or simply nh by 2 pi. The energy difference between those two particular layers will give you the energy of the emitted photon. Hey all, I am Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we were dealing with atoms. So in the previous session, we discussed about the famous model that is obtained from the alpha scattering experiment, that is Rutherford's nuclear atomic model. Now, we saw that there were some drawbacks to this particular model. Let's see how they got fixed. So again, the drawback of Rutherford's atomic model was that he did not define specifically how the electrons behave around the nucleus. And the way he explained that particular set of electrons revolving around the nucleus meant that they would radiate energy over the course of time and slowly spiral out of control and land in the nucleus, which is not actually a true fact. So again, he could not also explain the line spectrum of the hydrogen atom. So because of these drawbacks, his student actually came forward and put forth a new theory. That particular person was Niels Bohr. So again, Niels Bohr was learning the ways of the quantum mechanics, or simply learning how the atom actually functions, and he proposed several theories that actually made sense about the electron. So what did he propose? So the famous discoveries of Niels Bohr was restricting the electron to specific territories. For example, he said that an electron can only revolve through certain stable stationary orbits in which their angular momentum, that is the angular momentum of the electron, will be an integral multiple of h by 2 pi. Later, if you're studying physics, you will learn this constant to be h cross or h bar. Again, where h is the Planck's constant. So this is a mathematical constant actually. You'll learn it if you're studying physics even further. And again, if that is the condition, then we can say that the angular momentum L of that particular electron will be equal to an integral multiple of h by 2 pi, or simply nh by 2 pi. You can also equate it to the classical definition of angular momentum, which is mvr. So we can say that mvr is equal to nh by 2 pi. And Niels Bohr said that if electrons are restricted to these particular orbits, which is having an angular momentum of nh by 2 pi, then the electrons revolve in the stationary orbits without radiating any energy. That is, in the prediction of Rutherford, the problem was as they revolved around this particular orbit, the electrons will radiate energy and slowly fall into the nucleus. That was the drawback. If the electrons are restricted to certain stationary orbits, then we can say that they won't radiate energy until they change that particular orbit. That was Niels Bohr's second assumption. And the third assumption is that they will only radiate energy when they are jumping from a higher energy state to a lower energy state. And vice versa is also true. That is, they will absorb energy when they are jumping from a lower state to a higher state. So again, the assumptions of Niels Bohr is very simple. He assumed that, okay, around the nucleus in fixed stationary orbits, the electrons can revolve having an angular momentum of mvr, which is equal to nh by 2 pi. It should be an integral multiple of h by 2 pi. And they can only radiate energy when this particular electron jumps from a higher state to a lower state. When it is coming from a higher state, where this is the higher state and this is the lower state. This is the lower state. So again, when they are jumping from a higher state to a lower state, then only they can radiate energy. Other than that, they cannot radiate or emit any energy. And if they are jumping from a lower state to a higher state, then energy has to be absorbed. Somebody has to give them some energy so that they can jump. So again, this was the famous assumptions of Niels Bohr. The only thing you have to remember here more specifically is that when electrons jump from higher state to lower state, they radiate energy. This will play an important role in the coming session. So the next topic is line spectrum of hydrogen atom. So what exactly is this line spectrum? So just like we have our fingerprints, each atom will have its own definite characteristic, and this can be analyzed through line spectrums or simply atomic spectra. So here, what exactly is a line spectrum? So we can define a spectra as simply when an electron which is in a higher state jumps from that particular higher state to a lower state, it will emit a photon, just like Bohr's prediction. So when it emits that particular photon, it will have an energy difference between those two particular higher level and lower level. This particular process is termed as line spectrum of hydrogen atom, and there is a variety of spectra depending on from where the electron is actually jumping from. Is it jumping from the second orbit to the first orbit? Is it jumping from the third orbit to the first orbit? Is it jumping from third to second? Like that, depending on where the electron is jumping, there will be different kinds of spectra. So again, we can define line spectrum of hydrogen atom simply as when an electron makes a transition from the outermost orbit to the innermost orbit, then we can say that that particular transition is known as spectra, and simply the energy difference between those two particular layers will give you the energy of the emitted photon. So again, this particular idea Niels Bohr actually borrowed from the famous scientist, that is Einstein. So Einstein, in his famous photoelectric equation, actually equated frequency and energy into one single term and called it as E is equal to h mu, his famous photoelectric equation. Inspiring ideas from this particular equation, Niels Bohr actually formulated an equation and said that, okay, when an electron jumps from a higher state to a lower state, it will actually emit a photon of energy which is equal to the energy difference between the final shell and the initial shell. So for example, you can say that if this particular energy shell contains EF amount of energy and it is jumping to a layer containing EI amount of energy, then the emitted photon will have an energy of the difference between these two layers, that is EF minus EI. That is what Niels Bohr actually explained. So you can say that the energy of the emitted photon will be equal to this particular energy, that is EF minus EI, which means energy of the final state minus energy of the initial state. And now using Einstein's photoelectric equation, we can actually say that we already know that E is equal to h mu, right? We already know this from the previous chapter. So using this particular equation, we can actually say that h mu is actually equal to EF minus EI. So from this particular equation, we can actually even find out what is the frequency of the emitted photon. So again, we can say what is the frequency of the emitted photon, which is equal to EF minus EI divided by h, where h is the Planck's constant. So from this particular equation, we know what is the energy of the emitted photon and we know what is the frequency range of that particular emitted photon, which means that we can actually predict, okay, where the particular frequency range will be, what kind of photon will be emitted. So based on from where to where the electron is jumping and what kind of frequency it is producing, that is what kind of photon is being emitted, we can actually predict or we can actually define certain series. That is, the main series are Lyman series, Balmer series, Paschen series, and bracket series. You have Funt and Humphrey series also, but again, it is not of that much importance. But these are the main series: Lyman, Balmer, Paschen, bracket. So again, how are they differing and what are these particular series? So based on from where to where you are jumping, all of these series will come into effect. That is, if the transition is from N2 to N1, we call it as Lyman series. That is, if the final product, that is, if the final shell in which you are jumping to is the first shell, that is NF is equal to 1, then we can say that, okay, that particular series is going to be Lyman series. So from where all can this particular electron jump to the first shell? It can jump from n is equal to 2, right? It can jump from the second principal orbit to the first, or it can jump from 3 to 1, or it can jump from 4 to 1, or 5 to 1, or 6 to 1, or 7 to 1. Like that, how many layers are there? It can jump from any higher state to a lower state, which means the final state will always be nf is equal to 1. The higher states can differ, which means n can be 2, 3, 4, etc. So if this is the case, then we say that, okay, this belongs to the Lyman series. And similarly, for the Balmer series, nf will be equal to 2, which means the final orbit which the electron will be jumping into will be 2, which means anything about 2, the electron can make a transition to the final state, which is having a principal quantum number of 2. So we can say that n will be equal to 3, 4, and so on. Similarly, for Passion series also, it is going to be the third one, which is the final one, and anything above third is going to be the initial state. And similarly, there is bracket series also. So for each of these particular transitions, a different type of photon is actually emitted. So what kind of photon it is, what frequency it is, it will always be dependent upon from where to where this particular jump is happening. Is it from the n, let's say 7 to 1, or is it from 7 to 2, or is it from 7 to 3? Like that, from where to where this particular jump is happening will determine the energy of the photon, which in turn will determine the frequency of the emitted photon. So we know that there is a wide spectrum of radiation, which means it can be in the ultraviolet region, it can be in the visible light region, it can be in the infrared region. We don't know. Depending on the jump, it can actually be in any particular region. So we can actually predict based on from where to where they are jumping, that which region that particular photon or that particular energy of that particular radiation is going to be. So again, we can just simply define if this transition is from a higher energy state to the lowest most, that is, which is having a final number 1. If it is like that, we can say it is in the Lyman series. And in the Lyman series, the energy of the particular emitted photon will be in the UV region. And similarly, for Balmer series, where NF is equal to 2, the emitted photon will have a frequency range that is landing in between the visible region, which means we can actually see the effect of the Balmer series using our naked eyes. And Passion and Bracket series are going to be under infrared region, that is actually landing in the higher end of the wavelength. So again, we don't have to refresh everything like this. There was the equation of Rydberg constant and the equation to find out the wavelength also, but again, that was all discussed in the chemistry chapters previously, and it is not there in your physics textbook right now because it's been removed. But since we cannot predict how the NCERT is going to ask the questions, I'll just discuss 2 equations which are actually important for you. So again, we are not going to find out what is the wavelength of the emitted photon. We are just going to find out what is the radius of the nth orbit. So again, you don't have to know the definition and the intricacies of the derivation. You just need to know what is the equation itself. So if r is the radius of the nth orbit, then we can say that n square h square epsilon naught divided by pi m e square will give you the radius of the nth orbit. Always remember, where n is the principal quantum number, and h is Planck's constant, epsilon is, again, you already know from the first chapter, it is electrical permeability, and then pi is a constant, m is the mass of the electron, and e is the charge of the electron. So again, if you look at this particular quantity, there is one interesting relation also here. That is, other than this particular n, all the other numbers are actually fixed. which means that h is a constant. H is Planck's constant, it cannot change. Epsilon naught is another constant, it cannot change. Pi is a constant, it cannot change. Mass of an electron cannot change. Charge of an electron cannot change. Again, mass of any object can change when it is approaching light speed, but again, if the electron is already at light speed, it won't change. So again, we know that according to laws of physics, mass is not directly or suddenly going to change like that. So we can say that mass is also a constant, which means the only changing quantity is the principal quantum number. So we can just say that R is directly proportional to n square. This particular relation is also good to remember. That is, radius of the nth orbit will be directly proportional to the square of the principal quantum number. Or simply we can just write it as Rn will be equal to n square R1, where R1 is actually the radius of the first orbit. So again, this is good relations to be known, because if they ask a numerical problem, you can just simply directly substitute these values and just find out the answer. Similarly, we also can use this particular equation. That is, there is an equation in order to find what is the velocity and energy of the nth state orbit. So again, you don't have to know the derivation, you don't have to know how we got at the final result, you just need to remember the equation, and the equation states that the velocity is given by e square by 2 epsilon naught nh. And again, if you look at here also, the same relations seems to be forming. Again, all the other numbers are constants except for the principal quantum number. So we can just say that velocity will be inversely proportional to the principal quantum number. Just like that, if for energy also we can find a relation which states that En will be given by, energy of the nth orbit will be given by minus 13.6 divided by n square. Okay, this is obtained from a relation that is from the conservation of energy. That will actually prove that Ke will be equal to, that is, kinetic energy will actually be equal to the negative of the total energy, or simply potential energy will be equal to 2 times the total energy. This particular relation was mentioned in your textbook, but again, it is all in the deleted portions right now. But still they can ask an MCQ question or simply a numerical questions from these. So just to be on the safe side, we can just remember all these. So finally, in this chapter, we need to bring back one important personality, that is de Broglie. So de Broglie again propagated or hypothesized that, okay, matter will have wave characteristics. So when he heard that, okay, Niels Bohr is also applying this particular principle, he said that if electrons are circling or revolving around the said nucleus, then they should be, that is, if electrons are treated like particles, they should be exhibiting that particular matter waves that de Broglie actually defined. So we can say that electrons in the permitted orbits should be seen as particle waves. That is, again, in the previous chapter, whatever we said, he's just applying the same theory here. And again, the electrons are treated as waves. The only difference is that instead of the wave going like this, the wave is going to be expressed in a closed loop. That is, if you take a string, a rubber band maybe even, stretch it and give it a vibration, you can see the waves, right? So depending on that particular shape of the orbit will be having waves like this. So that is what de Broglie actually explained. He said that the electrons which is traveling around the orbit, around the nucleus in a particular fixed orbit, will be behaving like particle waves, and just like waves traveling in a string. If you take a string, stretch it and make it vibrate like a rubber band or something, then that particular vibrations will be similar to that of a particle wave in an electron, which just states that, okay, electrons are having wave characteristics as well as particle characteristics. So this is again de Broglie's theory being applied onto subatomic particles. So again, we can calculate and compare these two results. Is de Broglie right? And is Niels' assumption being shattered, or both are the same? So we can actually mathematically prove that they are one and the same. So again, Niels Bohr said that, okay, electrons are restricted to stationary orbits, and they are known as, and they will have an angular momentum of mvr is equal to nh by 2 pi. But now de Broglie is coming and saying that if electrons are moving in such a way, they should be treated as matter waves or simply particle waves, which means that we have to calculate a new result and see if he is agreeing with Niels Bohr or is he disagreeing with Niels Bohr. So again, if it is said to be traveling around the nucleus in a fixed path, and let's assume that it is a perfect circle. If that is the case, that is circumference of the orbit, that particular circle is the orbit, right? So circumference of the orbit must be equal to the integral multiple of its wavelength, because de Broglie hypothesized that it will be like a stretched out string which is vibrating, which means the circumference of the orbit will be equal to an integral multiple of its wavelength. Which means that 2 pi r, which is the circumference of a circle. We are assuming that the orbit is a perfect circle. So 2 pi r will be equal to n lambda. So this will be equal to n lambda. This is the primary assumption which we are taking. But we do know one more thing, that is, according to de Broglie, he has an equation for the wavelength, which we learned in the previous chapter. That is, lambda will be equal to h by p or h by mv, right? Lambda is equal to h by mv according to his particle wave hypothesis. So we can see that 2 pi r will be equal to nh divided by mv. So if I rearrange this particular equation, I can say that mvr is equal to nh divided by 2 pi. So when we go with de Broglie's hypothesis, we get the result mvr is equal to nh by 2 pi, which was the exact prediction of Niels Bohr, which is equal to the angular momentum of the electron in the stationary orbit, that is nh by 2 pi. So again, there is no contradiction. Both of them are agreeing very well with each other, which means his hypothesis also is very much plausible. So this was the conclusion of this particular chapter, that is known as atoms. And now again, it is not over. We examined what dual nature of radiation was, and again then we went into atoms, and now we saw what electrons are actually all about. Now still one more thing is remaining, that is the nucleus. So we'll be back with more interesting stories or more interesting experiments about the nuclei. But till then, it is all about atoms. I'll meet you all with a new chapter that is all about nuclei. I hope you have understood everything about atoms. I'll see you all very soon. Thank you.